Welcome to our deep dive into managing and responding to artificial intelligence incidents. This is episode 36 of our AI audit exam prep series, and today we are focusing on what happens when the alarm bells ring and your automated systems are under active attack. We will explore the three foundational pillars of incident response, which are containment, eradication, and recovery. Most importantly, we will dissect exactly why standard information technology playbooks fall short when dealing with the unpredictable nature of machine learning and what you must do differently. Understanding this is an absolute necessity for your professional career. When a crisis hits your corporate network, business leaders will panic. If you know how to safely isolate a compromised algorithm without taking down the entire company infrastructure, you become the crucial voice in the room. You will be able to evaluate if an artificial intelligence agent is truly secure enough to handle sensitive customer workflows, and you will know exactly what criteria must be met before bringing a repaired system back online. Let us begin by comparing traditional systems to modern automated models. In standard software, fixing a breach is usually a matter of patching a broken line of code or resetting a compromised password. Artificial intelligence, however, operates on probabilities rather than strict, unbending rules. Because these models are highly complex and interconnected, conventional strategies to lock down a threat are much less effective. The very first phase of any crisis is containment. Containment is the act of stopping an incident from spreading further into your environment. Think of a wildfire breaking out in a dry forest. Containment is not about putting the fire out completely. It is about digging a trench around the flames so they cannot jump to the nearby town. The exact actions you take depend on the situation. If an automated system controlling physical machinery goes rogue, threatening human life or safety, you must take immediate action to shut it down entirely. However, trying to selectively disable just one specific feature of a complex algorithm is often impossible because the internal mechanisms are deeply intertwined. Let us look at how containment works for three specific threats. First is prompt injection. This is an attack where a user inputs clever, manipulative text to trick the language model into ignoring its safety protocols. Imagine someone handing a bank teller a note that looks exactly like a direct order from the bank manager, tricking the teller into handing over cash. To contain this, we deploy data input and output validation, along with prompt templates. This means we place strict digital filters on what the user is allowed to type and what the system is allowed to respond with, effectively creating a protective shield around the core model to screen and sanitize abusive prompts. The second threat is data poisoning. This occurs when a bad actor intentionally inserts corrupt or malicious information into the massive datasets the system uses to learn. It is like secretly dropping a few drops of dark ink into a city water reservoir. To contain this, you must instantly revoke access to the datasets across all systems involved in the data pipeline. You must also block access to the computer scripts that process and prepare this data, stopping the toxic information from flowing any deeper into the system architecture. The third threat is adversarial inference. This is a methodical attack where someone repeatedly queries the system, analyzing the answers to reverse engineer its private training data. Imagine a detective interrogating a suspect for hours, using tiny changes in the suspect's story to uncover a hidden truth. Because these attackers use perfectly normal, validated channels, like an application programming interface or a standard user interface, you cannot just turn those doors off. Instead, you contain the threat by throttling. Throttling means artificially limiting how many questions a user can ask per minute, while simultaneously running heavy sanitization and validation checks on their inputs to disrupt their systematic probing. Once we have contained the spread, we move to the second phase, which is eradication. Eradication is the complete removal of the threat from the environment. Because we cannot just apply a standard software patch, the eradication technique depends entirely on how the attacker got in. To eradicate a prompt injection vulnerability, the underlying model ideally needs to be retrained or fine-tuned so it natively understands how to resist manipulation. However, for massive systems like large language models, starting from scratch is financially impractical and incredibly costly. Therefore, the long-term eradication strategy usually falls back on maintaining those rigid data validations and prompt templates we use during containment. Eradicating a data poisoning attack is a massive undertaking. You must meticulously hunt down the poisoned data, isolate it, and remove it from the training records. Then, you are forced to train a completely new version of the model, which is highly time-consuming. In the short term, you can sanitize the output to catch any bad behavior before it reaches the user. In the long term, you perform selective retraining. This is where you feed the system an overwhelming amount of fresh, clean data specifically chosen to overwrite the bad habits, forcing the machine to forget the poison concepts. To eradicate adversarial inference, we must modify the model itself using regularization and defensive distillation. Let us translate those terms. Regularization is a mathematical adjustment that stops the system from memorizing data word for word, forcing it to learn general patterns instead, which builds resilience. Defensive distillation involves training a secondary, smoother model based on the first model's general probabilities. It is like hiring a translator to speak for a politician. The core message is delivered, but the exact internal thoughts and secrets are hidden from the public. The final phase is recovery. This is the critical step of returning the automated solution to a safe, fully operational state. You only reach this stage after you have successfully verified that the threat is both contained and eradicated. However, the hard truth of artificial intelligence is that some attacks leave permanent marks and cannot be completely erased. Because of this reality, your optimal resolution is to drastically reduce the attack surface, giving malicious actors fewer entry points to prevent a relapse. You must set up active monitoring to catch any residual, lingering threats, and constantly build more robustness and resilience into the model over time. Before you bring the system back to life, you must implement stricter user access controls and entirely new layers of input and output guardrails. Most importantly, you cannot just turn the machine back on and hope for the best. You must conduct a rigorous post-incident validation. This is an exhaustive test of all your new security measures. Only after this validation proves successful and you have obtained explicit approval from all relevant business stakeholders, are you allowed to reactivate the artificial intelligence solution. Let us review our core concepts. Automated models are too complex for traditional incident response to work perfectly. Containment focuses on stopping the immediate damage, whether that means throttling user queries or completely revoking dataset access across the pipeline. Eradication is about rooting out the vulnerability, often requiring creative solutions like selective retraining or defensive distillation because full retraining is too costly. Finally, recovery demands that we reduce the attack surface, implement stricter guardrails, and secure executive approval before turning the system back on. To understand how these concepts and techniques are tested in the exam, I encourage you to visit RooCloud.com. Every concept we discussed today is featured in the comprehensive multiple choice questions on the platform. Solving these chapter-wise questions is the best way to solidify your understanding before we move on to the next topic. Thank you for your time, and I will see you in the next episode.